side A because the compressors noted them as compressor A for side B and compressor A for side A. So it was only logical to do that. Here is a profile view of the towers. There's 4 per side. This side is side A, so you can see how approximately tall and wide each tower is. You can see compressors here, there. On the other side, it's kind of nice looking thing, not too big or small or anything. Here's one of the compressors. Right there, it's noted that that is cold. I believe that is because it's before compression. Here is the other compressor after it's been compressed. That is hot. Here is the system model for a similar cycle where you have the refrigerant going around and then the refrigerant gets cooled by the air heat exchanger, which is what the fans blow air from, which way to cool it, and the water heat exchanger that runs throughout the building of the Challenger Center. So the heat transfer rate was found with energy equation where Q prime equals mass times the C, the constant, pressure coefficient. I don't know why that's there. It's not pressure coefficient. I thought I changed that. It's the
heat capacity.
The heat capacity of the air, and then the delta T is change in temperature. So the mass flow rate is found by density times the volumetric flow rate. And so first we're going to find out what the density is. For human air, I found this calculation online where rho is equal to the total pressure in pascals divided by the gas constant for dry air, which was 287.05 joules per kilogram Kelvin, and the temperature. Then it's multiplied by 1 minus the partial pressure of water vapor in air, and then the total pressure again. So to find the partial pressure of air, you multiply the partial pressure of water times the relative humidity to get this, which is really complicated. I don't know if you want me to go into it, but it turned out really accurate. I don't know about that. Unless you want to look at it, because,
where did it come from?
Where did what come from?
This.
Oh, it's referenced online. It's like some site, but from all this and all the other sources I found, this is the only way I could actually find the equation, because I used a calculator to find the density, and this actually worked very well compared to all the actual references, and this is just to calculate it. So with P equaling that, we found out plug that into the equation before, where 72% humidity and 0.796 raised to the 8 was 37.8 hectopascals. So plugging that back into the density equation, we get 1.16 kilograms per cubic meter, which then converted to pounds per cubic inches was 0.000419 pounds per cubic inch. So now that we have the density, we have to find the volumetric flow rate, where do this, we found each volumetric flow, or the speed of the air velocity at each radius, which then we multiplied the velocity by the radius to get a total correlation. And by doing this, for one reason or another, integrating that, that's the graph. As you can see, it goes up the farther the radius goes out. So then the mass calculation is you integrate this between each 2 points to get a volume, and the volume is based on speed, so then it is a volumetric flow rate, which I thought was interesting. Here is an example of before. This is how it was integrated, where this is the V times R, and each one of those are the areas under it, and then the sum of the areas was 1,770,000. And so with the volumetric flow rates times the density, we get 41 pounds per minute for one of the fans. So to find the heat transfer rate, we have to find the specific heat capacity of the air, which is humid. So to do this, I found this site from Perry's, or this equation from Perry's, where the coefficient of, or what's the coefficient? Why do I keep thinking that? The specific heat capacity is the heat capacity of dry air plus the absolute humidity times the heat capacity of water, which was calculated out. I used the psychrometric charts to find the absolute humidity, which was around 0.015 pound per pound. And then calculating those out, the specific heat capacity of water was 0.247 BTUs per pound per degree Fahrenheit. Here's an example psychrometric chart. It's kind of hard to do this one because it's really small. So with all the variables found out, I found out the Q transfer rate was 33.41 BTUs per minute per fan. So with multiple fans, all the air velocities aren't the same, so to take and get a better idea of how the system worked, I found an average flow rate for all the fans, which was done the same methods as before, but with data from all the fans. So with a V average of 1,333,000 cubic inches per minute, I found that all the Qs were averaged were about 40.5 BTUs per minute. So now doing 100% humidity, because we were interested in what would happen when you took the airflow readings when it was raining, we got these charts, which is pretty much the same as before, the same shape, but it's a little bit higher. And for the V times R, similar shape as before, but when calculating it out, the Q for 100% humidity, the energy transfer rate was 156, which was a lot higher than before. So because of that, there might have been some kind of correlation between the humidities and the heat transfer rates. So looking at the compressors, there's there's some data here. Like basically some of the interesting things out of this is that, you know, one's always running or the other's not for one reason or another. That you have the running times and then you have the running times, and these are all pretty much taken around the same time. So throughout the entire week, I found that side A was running from this many hours per week, and side B was running 98 hours per week. Actually, it wasn't per week, it was per 6 days, because we didn't take it on Thursday the week before rotation. We ended on 1 day. So it was 104 hours. So to do this, we took the percent running time of each over that amount of time. So side A was running for 28.5% of the time, and side B was running for 68.1% of the time. So they both were running at about 96.6% of the time, which is practically always running. So we're just going to use that as an assumption. So this is the data taken over a week's time of the changes of temperature between the tops and the bottom of the cooling tower. So basically how much temperature was transferred, or how much the delta T was for an entire week. And side B is always lower for some reason. Not always, but looks about that way. Pretty much all the time, even though it is running the most. So there's no way for me to figure out exactly why that is, but I don't know what else there is to do. Like, you can't even tell when it's running, really, compared to A or B. So I thought that was interesting. But because of that, I just averaged the entire changes in temperatures over the period of time, and got these delta temperatures to use for later. These are the humidities, because that might have had some effect on the heat transfer rate. And you can see that during the night it goes up, and during the day it's lower. Because this was taken in the afternoon at time 1 all the way to 7, which was when it was raining again, where the humidity went to 100. Since humidity is relatively similar, calculate those out to be about 61% over the course of the entire week period, and 67%. So using an average volumetric flow, 57, which was calculated before, and the run times of each, the QAs and QBs were calculated out to be 27 BTUs and 16 BTUs per minute. And then adding those up, it was 43.8 BTUs per minute per fan as an average. So that times 8 would be the total Q transfer rate. Here are my references. Are there any questions?